Hello everybody and welcome back. Today we are starting Unit 2, which is all about plate tectonics. So we have already talked about the Earth in relation to its position in space and also its role as a body in space. So now we're moving on and we're going to focus on the Earth itself and kind of dive into its composition and how our crust moves and how earthquakes are made and how volcanoes are formed and all the fun stuff. So we're going to go ahead and get started today with layers of the Earth. As always, you should have downloaded your interactive notebook pages for the day. And we are starting a new unit, so you guys will have a new title page as well as new vocab at the beginning as well. So let's go ahead and jump into our guided notes for the day. Today, like I said, we are talking about the layers of the Earth. And so really we're going to focus on Earth's interior. So Earth's interior consists of 3 major zones, and each one is defined by its chemical composition. And the 3 major layers of the Earth are the crust, the mantle, and the core. So let's first start talking about the crust. And this is where we live. So this is the solid rock. It is the thin, rocky outer layer of the Earth. So if you step outside your door and you step out onto the ground, you are standing on top of the Earth's crust. This is divided into 2 types, and it's going to be very important for us to know the 2 different types, especially when it comes to talking about plate boundaries. So we've got continental and oceanic crust. Continental crust is pretty thick. It's the thicker of the 2. It can be anywhere from 8 to 75 kilometers thick, but on average it's about 40. So this is the thicker crust, and it consists mostly of granitic rock. So basically it just means that the majority of the crust is composed of granite. And then we have oceanic crust, which is roughly 7 kilometers thick. So of the 2 crust types, oceanic is the thinnest, and this is consistent mostly of basalt and gabbro, and these are just 2 different mineral-based rocks that are composing our crust. So again, when we talk about continental crust, so when I say continental crust, I mean this is the crust that's on the land, okay? We live on the continental crust. And then the oceanic crust is the crust that's located beneath our oceans. Okay, so that's the only difference between the 2. And also, as a reminder, the continental crust is thicker than the oceanic crust. So the next layer that we're going to be talking about is the mantle. And the mantle holds 82% of the Earth's volume. It's a solid, rocky shell that sometimes acts like a liquid with plastic-like flows. So the mantle can move. So basically temperatures get so hot that the rock in the mantle melts and becomes this fluid-like substance. And this is going to be really important to keep in mind because this is what's going to drive plate tectonics. So this is what is going to drive basically most of the processes that we are learning about in this unit. The mantle extends to a depth of 2,890 kilometers. That's a long way down. And the dominant rock in the upper mantle is peridot and is composed mostly of silicon and oxygen, and those are 2 elements on our periodic table. So the mantle moves kind of like a lava lamp. This little animation doesn't work in this slide. But if you've ever seen a lava lamp, you know that like the goo inside is kind of all concentrated at the bottom before you turn it on. And then once you turn the lava lamp on, the little light bulb that's inside will heat up the goop and it'll start to slowly rise up, right? So it'll kind of separate from itself, it'll rise to the top, and then when it gets to the top of the lamp, that little goo inside, it moves away from the heat, so it cools down. It becomes more dense, and then it sinks back down to the bottom. And then as it gets closer to the light bulb, it heats up again. Then it will rise up, and it will go in this cyclical motion as long as the lava lamp is turned on. That's the same, basically the same basic motion of what happens in our mantle, and these are called convection currents. We talked a little bit about convection in our energy lesson of our Unit 1. but it's just that substances, when they heat up, they rise up. As they get away from their heat source, they cool down, become more dense, fall, and then they move in this circular motion. And this drives the movement of our plates, which we'll talk about a little bit more in future lessons. The next layer that we're going to talk about is the core, and this is a sphere composed of an iron-nickel alloy. It's similar in composition to metallic meteorites, and the temperatures range from 5 to 7,000 degrees Celsius. That is hot, 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 hot. We would not be able to drill to the center of the earth, and we as humans go down there because our bodies are just not made to withstand that type of temperature. I think there was a movie where they tried to like drill to the center of the earth to like save the earth or something, but it was silly. We can't do that. We don't have the technology to do that. So here's a depiction of our layers. So again, we've got the crust, the thin part on the outside. So like anywhere you see land, this is continental crust, and then the oceanic crust will be beneath the oceans. The mantle makes up the bulk of the volume of the earth, and then we have our core. And our core is composed of an outer core and an inner core, and we'll get to that in just a second. So we need to be aware of certain layers of our Earth. There are layers that are kind of categorized based on the 3 layers we're already learning about. But the first one is our lithosphere, which is the crust and the upper portion of the mantle. So the mantle is not all liquid. There is a solid portion of the mantle. So if you ever see us referring to the lithosphere, this is just the crust and the upper portion of the mantle, so the solid part. And this is about 100 kilometers thick. Next, we have our asthenosphere. This is also part of the upper mantle. The temperature and the pressure cause the rocks to easily deform like hot wax or silly putty. Okay, so this is where we're getting those convection currents starting to occur because we've got the deformation of the rocks due to the heat. And then the lower mantle, this is from 660 kilometers down to the base of the mantle. This is a rigid layer. The rocks are still hot and can flow gradually, so the movement won't be as great in the lower mantle as we have in the asthenosphere. And then our core, a lot of times we'll just refer to the core as one single layer of the earth. So you have the crust, the mantle, and the core, but the core has an outer and an inner core. So the outer core is a liquid layer that is 2,260 kilometers thick, and this layer is thought to generate the Earth's magnetic field. So remember, we learned about our magnetosphere in our astronomy unit, and it protects us from solar wind. The inner core is the sphere with a radius of about 1,220 kilometers, and despite the high temperature, this area is solid because of the intense pressure. So the whole reason we even have basically liquid rock in the layers of our Earth is because it's very hot. The inner temperature of the Earth is hot, but in the inner core, there's so much pressure. We know that because of this, the inner core has to be solid because the pressure of the Earth working on it causes it to solidify. So there's a solid ball at the center of the Earth with an outer liquid core. Temperature and pressure increases as you go further down the layers. So as you get closer, so through the mantle to the core, you will find higher temperatures and higher pressures. But if we can't see the inside, if we can't drill to the core, how do we even know that there's a liquid outer core? Keep that in mind. And then here is just a cross section. So this is called a cross section. It just kind of is like if you were to take a slice of cake out of the earth, this is what it would look like. So here we have our lithosphere, which is our crust and our upper part of the mantle. And then again, our asthenosphere, which is that liquid part. So going back to the question, how the heck do we know that the outer core is actually a liquid? Well, we know because of something called seismic waves. And these are just vibrations that travel through the earth, and they are typically caused by earthquakes. There are 2 main types of seismic waves. You've got P waves and S waves, and we will talk more about these waves when we talk about earthquakes. But in relation to our core, We know that the outer layer of the core is a liquid because S waves can't pass through liquid. So scientists can measure waves as they pass through the Earth, but what they find is that the S waves are basically deflected around the outer core because they can't pass through it. And so this would be the indication that our outer core is liquid. So even though we can't drill down there and we can't see the outer core, we know because these waves can't pass through it that it has to be a liquid. And then there's something to be aware of called the Mohorovic discontinuity. It's more likely referred to as the MOHO discontinuity or the MOHO boundary, because that's just a mouthful to say. But this is just the area between the crust and the mantle. So, and in this area, velocity of seismic waves increases abruptly, and we'll talk about that a little bit more when we get to earthquakes. But really what you need to know for the MOHO boundary is that it is the area between the crust and the mantle. And these are just some interesting facts to wrap up our lesson for the day. Density is something we didn't talk about at the beginning of our class, but density is something that you'll probably deal with a lot in many of your science classes. And this is just a measurement of mass divided by volume. And density will basically determine how well a substance floats, right? So if you're less dense, you will be more likely to float on water. So if your density is less than the density of water, then you'll be able to float. The density of the Earth is 5.5 grams per centimeter cubed. Neither the sun's heat nor winter cold can penetrate the Earth below 20 meters. So that radiation from the sun being absorbed, it doesn't really matter how it's heating up our atmosphere and how we experience temperature. It's not going to affect the layers of the Earth. At 20 meters above, the temperature is relatively the same as the surface temperature, except where there are volcanoes and hot springs. And then below, the temperatures increase 1 degree every 40 meters. So remember, as you go towards the center of the Earth, both temperature and pressure are increasing. And that's it. So that is the end of your Unit 2, Lesson 1. This was a pretty quick one. You guys have a assignment to complete today. And of course, as always, if you have any questions, just reach out and let us know. But other than that, that wraps up this lesson.